Assalamu alaikum dear students. So today we are going to learn how to evaluate double integrals over general regions. That is the regions which are not rectangular regions. Uh, these are called general regions. So this is how you can see general region looks like, which is not a rectangular region. So there are two types of general regions in terms of limits of variables. So first type is called type 1. In this case, x lies between some interval constant values, where y lies between two functions of x, where these two functions of x are continuous in the closed interval AB. So there are few examples of this type. So in this case, you can see that in this region, x lies between A and B, where y is bounded below by this curve and bounded above by this curve. So if you draw vertical lines in this region, so you can see that every line enters the region from this curve, which is called lower curve, and exits the region from this curve, which is the upper limit for y. So there is another example of type 1 region. This is another example of type 1 region. And once we have limits, so how to write an iterated integral? So the corresponding integral, that is double integral of the function fxy over the region D, which is defined by this region, can be written in this form. So since x is constant, x lies between two constant values, so we'll integrate first with respect to y, and then we'll integrate with respect to x to have a constant value of this double integral. And in type 2 region, y lies between two constant values, that is y lies within an interval, say CD, and x lies between two functions of y, where h1, h2 are continuous functions in the interval CD. So there are a few examples of type 2 regions. Now in this case, the y lies between C and D, that is lower limit for y is C, upper limit for y is D, where if you draw horizontal lines in the region, anywhere in the region, you can see that these lines enters the region from this curve, that is left curve, and exits the region from this curve, that is the right curve. So right curve is the upper limit for x and left curve is the lower limit for x, because values of x increases in this direction. There is another example of type 2 region, and corresponding iterative integral can be written in this form. Now since y is constant, so you can see that outer limits are for y, and we are going to integrate with respect to x first, and then we'll integrate with respect to y. So let's learn the process of integration and finding limits for x and y with the help of few questions. So this is question number 13 in the textbook, and section is 15.2. So in question number 13, we have to integrate this integral over the region D, where D is enclosed by the line. So first of all, let's draw the region to understand the limits for x and y. So first line is y is equal to x, and that is the line which bisects the plane and passes through the origin. So this is origin, and this is y is equal to x. Next line is y is equal to 0. Y is equal to 0 is the line that is x-axis, of course. Y is equal to 0. And x is equal to 1 is the line, vertical line, and passing through this point 1 0. So this is 0 0 point, and this is 1 0, and this point is 1 1. Now this is the region D, which is bounded by these lines. Now in this region you can see that minimum value of x is 0 and maximum value of x is 1. So x lies between 0 and 1, and these are type 1 limits, and y is bounded by these two lines. If we draw a vertical line here, or like this, any vertical line in the region, you can see that this is the lower limit for y and this is the upper limit for y. So along this line y is equal to 0, it means y is greater or equal to 0, and along this line y is equal to x, this is the upper limit for y, so y is less or equal to x. So these are type 1 limits. So for type 1 region we have these limits. Now see type 2. For type 2 we have to find an interval for y. Again we'll see what is the minimum value of y in this region and what is maximum value of y. So let's draw this line. This is the maximum value of y, so maximum height of any point in the region, and here y is 1. So this point is 0 1. So y lies between 0 and 1, whereas x lies between this line and this line. So if you draw horizontal lines, you can see that this is the line where through which this horizontal line enters the region, and along this line value of x is y. So lower limit for x is y, and these lines exit the region through this line, and along this line x is 1, that is x is less or equal to 1. This is upper limit for x. So this is how we can determine type 1 and type 2. So let me solve this integral for type 1, and you can solve type 2 integral yourself. So let's start. This is the region D and x dA, and this for type 1 this is the region D. So let's write associated iterated integral, and since x is constant, so we are going to write limits for x here, and then we'll write limits for y 0 to x, and function to be integrated is x, and since internal limits are for y, so dy comes first and then dx. Okay, let's solve 0 to 1, and since we are going to integrate this with respect to y, so x will be kept constant and this will become xy. The limits for y are 0 to x. Let's plug in the limits. We have when y is x, it becomes x square. When y is 0, it becomes 0. So we are left with x square dx. And its integration is x cube over 3, 0 to 1. And this is equal to 1 over 3. So this is the answer. So for type 2, you can write this integral as I'll write the iterated associated iterated integral, and then you will solve it yourself. So let me write. This becomes, now since for type 2 region D can be written in this form, so since y has constant limits, so we'll write limits for y first and then limits for x y to 1, and our function is x, so dA in this case becomes dx dy. So do it yourself and you will get same answer. If you don't get the same answer, it means you would have done some mistake in the process. Okay, let's solve. Question number 14. Again, I'll discuss both the types, type 1 and type 2, but I'll solve one of them and you can solve other yourself. So let's draw the region first of all. That will make the process easier. We have these two curves. So this region D, we have to integrate this function over the region D, where D is enclosed by these curves. So first of all, let's draw. We have y is equal to x square. So this is the parabola like this. This is symmetric about y-axis. So this is y is equal to x square. And this is the line y is equal to 3x with the gradient 3 and passing through the origin. Now we have to find these 2 points of intersection. Our region D is actually the region between these two curves. So this is the region D. So in order to find the limits, we have to find the points of intersection. Y is equal to x square, y is equal to 3x. So for intersection x square is equal to 3x. So this becomes x square minus 3x is equal to 0. Let's factor x out. So x times x minus 3 is equal to 0. So this actually gives us two values for x. X is 0 or x is equal to 3. When x is 0, y is 0. And when x is 3, y is 9. So these are the points 0, 0. And this point is 3, 9. Okay, now we have to find the type 1 and type 2 regions. And for type 1, x lies between two constant values. So minimum value of x in this region is 0. And this is the maximum value of x, and at this point x is equal to 3. So this is 0, this is 3, 0 point. That is, x lies between 0 and 3. Okay, in order to find the range for y values, so we again have to draw the vertical lines. So you can see that this region is bounded below by this curve, which is x square. So y is more than equal to x square, and this region is bounded above by this line, along which value of y is 3x, so y is less or equal to 3x. So these are the type 1 limits. And type 2 region, that is, this is t. And for type 2, y, variation for y, so we have to find the range for y values. So let's draw a horizontal line here. So y values are bounded by these two lines. That is, y lies between 0 and 0 and 9. So y lies between 0 and 9, because at this point y is equal to 9. Okay, now for x values, we can draw horizontal lines, and you can see that every horizontal line enters this region through this line, and along this line value of x is y over 3, because y is equal to 3x, so x is equal to y over 3. So x is bounded below by y over 3, and this is the right curve, this one. So along this, x is equal to square root of y. Because x is positive, so we are going to consider this positive branch, that is, x is less or equal to square root of y. So these are the regions of two types. So this is region D along region D of type 2. So for the integration process, let's write iterated integral for both of the types. So type 1 iterated integral would be, here we have x lies between 0 to 3. So we are going to write this first, and then y lies between x square and 3x, and then we have xy. So interior limit is for y. So we are going to integrate with respect to y first, and then we'll integrate with respect to x. Similarly, type 2, and you can integrate it yourself, so rest of the work can be done yourself. So type 2 iterated integral would be, in this case, y lies between 0 and 9, so we are going to write limits for y first, 0 to 9, and then x lies between y over 3 and square root y. So in this case, we are going to write dx dy. Again, do it yourself, so you can integrate it yourself. So the most important and the crucial thing in such type of integrals is to find right limits. If once you have limits, rest of the process is just exercise for integration, and you can solve it very easily yourself. Okay, let's try a few more questions to understand the idea. So in this case, we are just required to evaluate the double integrals, and let's try something different. That is question number 19. So in question number 19, we have to integrate this y square over the region D, where D is the triangular region with the vertices 0, 1, 1, 2, and 4, 1. So again, in order to find the region, we have to draw the region. Let's first draw these points. 0, 1 means x is 0, y is 1, so this point lies somewhere here. This is 0, 1. 1, 2, x is 1, y is 2, so this point is somewhere here. One, 2, and 4, 1. So 1, 2, 3, and 4. 4, 1, that is somewhere here. Okay. 4, 1, that is 0, 1, that this lies on this line. So 4, 1. This line would be horizontal line. And let's draw this. So this is the region D, bounded by these lines. This is a triangle. This is a triangle region, which is D. Now we have to find the limit. So in this case, type 2 would be easier for us, because if we find y in terms of x, you can see in this part, upper limit for y is this line, but for this part, upper limit for y is this line. So in order to avoid the confusion, you can choose type 2 for this. Type 2. Y lies between, so minimum value for y in this region is 1, and the maximum value for y in this region is 2. So y lies between 1 and 2. Whereas x lies between these two lines. If you draw horizontal lines, so you can see that y lies between these two lines, x lies between these two lines. That is, lower limit for x is this along this line, and upper limit for this line. bounded, x is bounded, in other words, x is bounded below by this line passing through 0, 1 and 1, 2, whereas bounded above by this line passing through 1, 2 and 4, 1. So we have to find the equations for these two lines first, and then we'll see what would be the upper and lower limit for x. So for this line passes through 0, 1 and 1, 2. So using 2-point formula, we have y minus 1 is equal to negative 1 divided by 1. So gradient is 1, and x minus 0. So this is equal to y is equal to x plus 1. So this is the equation for this line. And for this line again, use the same process. Y minus 1 is equal to, so 1 minus 2 is negative 1 divided by 4 minus 1. So negative 1 by 3 is the gradient of this line, and we have x minus 4. So this is the reference point. Y minus 1, x minus 4 times gradient, and gradient is 1 minus 2 divided by, rise over run, 1 minus 2 divided by 4 minus 1. Or we can simplify it like y minus 1 is equal to negative 1 over 3 x plus 4 over 3. So y becomes negative 1 over 3 x. 1 plus 4 over 3 is 7 over 3. So these are two lines. Now we have to find limits for y. So x is bounded below by this. So along this line, x is y minus 1. And along this line, x negative 3, 1 over 3. So x 1 over 3x is equal to negative y plus 7 over 3. So x becomes negative 3y plus 7. It means x lies between, this is the lower limit, x is y minus 1, and this is the upper bound, so x is less or equal to negative 3y plus 7. So these are the limits for the region, and this is type 2 region. Rest you can do yourself. Let me write the iterated integral, corresponding iterated integral, and we will be writing x 1 to 2. Y lies between 1 to 2 and x lies between y minus 1, negative 3y plus 7, and we have to integrate y square, and with respect to x first, and then we'll integrate with respect to y. And rest of the work can be done by yourself, so do it yourself. All right. Okay, similarly, you can try question number 20. So this its region is circular. So let's see how to solve this. So let's draw again. So region D is enclosed by the quarter circle. Y is equal to square root of 1 minus x square. So if we square both sides, we have y square is equal to 1 minus x square. That is x square plus y square is equal to 1. So this is the circle, and it's the quarter in the first quadrant. So let me draw. This is 1. This is 1. So this upper half is actually y is equal to positive, upper half represents positive values of y, and y is equal to square root of 1 minus x, and lower half of the circle actually represents y is equal to negative square root 1 minus x square. So since we have this positive value, so this is the upper half, okay? And x is greater or equal to 0. This is the condition on the region, so it means this lies on this side of the plane, that is right side of the plane, and this is bounded by x-axis. So we are going to have this region which satisfies all these conditions. So this is D. This quarter is the region D. Now for limits, so here we have 1 0 point, this is origin, and this is 0 1 point. And along this curve, we have y is equal to square root of 1 minus x square. Okay, so if we go for type 1, then we can see that x lies between minimum value of x here is 0, maximum value here for 1. So bounds for x are 0 and 1. So x lies between 0 and 1. Whereas bounds for y can be determined by drawing these vertical lines. So you can see that y is bounded below by this line, and along this line y is equal to 0. So y is more than equal to 0, and y is bounded above by this curve. So along this line, y is equal to square root of 1 minus x square. So this iterated integral can be written as 0 to 1, 0 to square root of 1 minus x square, and function to be integrated is xy, and our dA would be dy dx. So solve it yourself. Okay, there are a few more questions. We have to find the volume of the given solid, and we know that volume is the area, volume is the double integral of the surface along the region D. So for this we have to identify the surface fxy and the region D, type 1 or type 2. So under the plane, first question is find the volume of the given solid under the plane 3x plus 2y minus z is equal to 0 and above the region enclosed by the parabolas. So region D actually is defined by the region between these two curves, and fxy can be extracted from this equation, that is value of z would be fxy in this case. So fxy or z is equal to 3x plus 2y. So we are going to integrate this over the region D, and D is the region. Let's draw the region. D is the region, y is equal to x square is the parabola. Yes. And x is equal to y square. This is y is equal to x square. And x is equal to y square is this parabola. Symmetric about x-axis. So this is the region bounded by these. That's it. This is the region, and this is x is equal to y square. And first of all, find the point of intersection. Y is equal to x square and x is equal to y square. So substitute y is equal to x square here. So we have x is equal to x to the power 4. And 0. So x times x cube minus 1 is equal to 0. So we have x is equal to 0, and the real factor from this is x minus 1. So the quadratic factor does not actually give us real values of x. So the only two real values for this equations are x is equal to 0 or x is equal to 1. So when x is equal to 0, the point of intersection is 0, 0. And when x is equal to 1, y is also equal to 1. So this point is 1, 1. Okay, so if we consider type 1, then x lies between 0 and 1. And y is bounded below by this curve, and this curve is y is equal to x square. So y is bounded below by x square, whereas y is bounded above by this curve, and this is since positive branch of this curve. In this curve or in this branch, we can see that y is positive, that is this lies above x-axis. So y is equal to square root of x along this path. So let's write this: y is bounded above by square root of x. And volume is finally integrate this fxy, that is a volume under the surface above this region is given by this formula. So surface here is 3x plus 2y. So we have to integrate over this region D, and let me write this region D using type 1. So x varies from 0 to 1, whereas y varies from x squared to square root of x. And dx here is dy, dA here is, sorry, dA here is dy dx. So by solving this, you can have the volume. So do it yourself. So I hope you understand the idea. So let's discuss few more questions in terms of types of values of variable, and let's see which question we can in question number 27. So let me discuss few questions quickly. In question number 27, you can see that you have to find the volume of the tetrahedron enclosed by the coordinate planes. That is, coordinate planes are x is equal to 0, y is equal to 0, z is equal to 0. So for this you have to integrate, that is, we have to identify the function, the surface in terms of as there's a function of x and y, so that we can integrate this in order to find the volume fxy over the region D. So we have to identify two actually one surface and the other region. Okay, let's find out the surface first. So z here is, so let me write one by one. Z here is 4 minus, this is the equation of the plane, 4 minus 2x minus y. Okay, and let's identify the region. So first of all, the projection of the region on xy plane. So the plane x is equal to 0 and z is equal to 0, that is this is the line x is equal to 0, that is this line. Similarly, from y is equal to 0 plane and z is equal to 0 plane, intersection is x is y is equal to 0 line, so that is y is equal to 0 line, and intersection of z is equal to 0 and this plane, 2x plus y plus z is equal to 4 is the line, 2x plus y is equal to 4. So let's draw the line. 2x plus y is equal to 4 means when y is equal to 0, intercepts, its x and y intercepts are y is equal to 0, so x is equal to 2. Here is the point. And when x is equal to 0, y is equal to 4 somewhere here. So let's try this. Draw the line. Okay, so this is the line. And here we can write y is equal to 4 minus 2x. This is the equation of the line. Okay, and let's find out. Let me write this. This is 0, 4 and this is 2, 0. Okay, this is a region D bounded by these lines. Okay, so we can see that x lies between 0 and 2. So let me write 0 and 2 here. And y lies between this line and this line. So y is bounded below by this line. Y is bounded below by this line. That is why a lower limit for y is 0. And y is bounded above by this line. And along this line, y is equal to 4 minus x. So we can write 4 minus x here. So dy dx, because these are the limits for x. And you can evaluate the volume. This is the volume of tetrahedron. Similarly, you can see question number 26. In this, we have to find the volume enclosed by the paraboloid and the planes x is equal to 0, y is equal to 0, z is equal to 0, x plus y is equal to 2. So let's try the region. This is question number 26. Okay. So first of all, volume is equal to, we have to identify the function, and function is this. So we have to integrate this, x square plus y square plus 1. And in order to identify the region, let's draw the region on xy plane. Okay, when x is equal to 0 and z is equal to 0, its intersection is the line x is equal to 0. This is the line. Similarly, y is equal to 0 and z is equal to 0. This is the line y is equal to 0, and x is equal to x plus y is equal to plane, and z is equal to 0. Plane has intersection the line x plus y is equal to 2. So let's draw this. X plus y is equal to 2. Its intercepts are when y is equal to 0, x is equal to 2. So this is the point 2, 0. And when x is 0, then y is again 2. So this is the point 0, 2. And let's join the points. Okay. So this is the region. And again, we can see that x varies from 0 to 1 and y varies from 0 to this line. And this line is x plus y. So y along this line is 2 minus x. So we can write 0 to 2 minus x and dy dx. And integrate it yourself to find the volume. So do it yourself. So I hope that would be enough to understand the idea how to evaluate double integrals over general regions. So that's all for today. Bye.